this pack about? This pack is actually about harnessing the energy that is generated during redox reactions. So when we think about a redox reaction, so let's have a think about this reaction of copper sulfate with zinc. So on the left hand side in this little beaker we've got some blue copper sulfate solution and some zinc metal, and if we leave that for a while, over time what will form is some zinc sulfate and some copper. So there must be some redox going on there. Why don't you have a look at the oxidation states and see if you can work out who is gaining and who is losing electrons. So if we have a look at that, we can see that zinc is losing electrons because it's going from 0 to +2, and the copper is going from +2 to 0, it's gaining 2 electrons. So let's just have a look at that in a bit more detail. So in here we've got our copper sulfate solution. Now we know that that is made up of, it's composed of copper 2+ ions and sulfate ions. And we're not interested in the sulfate ions, they're spectators. And we've got zinc metal. Now we said on the previous page that zinc was losing 2 electrons. So we're moving electrons from here to here. 2 electrons are moving from Zn to Cu2+, so that we're transferring electrons so that at the end we would end up with some Zn sulfate, which actually is composed of zinc 2+ ions, and sulfate ions are still floating around, colourless spectator ions, and some copper metal. And so we've changed the copper 2+ ions into copper metal, and there's like a browny solid at the bottom, and we've given away electrons from the zinc and become zinc 2+ ions, and they're floating around in the solution and they're colourless. Now what we need to do if we want to harness that electrical energy is we need to have some way of getting those electrons to travel through a wire. If they could travel through a wire, rather than just going straight from the zinc to the copper, if they could travel through a wire, we could connect that wire to our light bulb, our mobile phone, and we could use that to power our equipment. And that is the essentials of a battery. So this is all about creating batteries. We need to get those electrons to travel through a wire, not just straight from one chemical to the next. So how do we do that? So this is what an electrochemical cell is. That's what a battery is. It's an electrochemical cell. It's going to use the electron transfer to produce electrical energy. So the electrochemical cell is going to be made up of 2 half cells. So we need to separate these 2 reactions, these 2 things that are going on here and here. We need to separate them so that we can put a wire between them and get those electrons out and transfer them through a wire. We're going to call the 2 halves half cells, and each half cell is going to correspond to one of the half equations. Okay? So a half cell is quite simply a beaker, and it consists of 2 species of the same element that are in different oxidation states. So our copper half cell is made up of our copper sulfate solution and a strip of copper metal. And you can see a picture of that set up on the side, on the right hand side. So we've got 2 species, copper and copper 2+. Okay, so the copper sulfate contains Cu2+ ions. And we do tend to have that as a concentration of 1 mole per decimeter cubed. It doesn't need to be copper sulfate as long as it contains copper 2+ ions. That's the +2 oxidation state, and the metal is the 0 oxidation state. And then the zinc half cell, very similarly, we can make our beaker, and we're going to put our 1 mole per decimeter cubed zinc 2+, so maybe we use zinc sulfate, maybe we use zinc nitrate, and then we're going to have our piece of zinc metal. And you can see a picture of that on the other side. These 2 half cells represent the half equation, and notice at the star box at the bottom it says the IUPAC convention for writing half equations in electrochemical cells is to give them always as a reduction. So if we were to give this as a reduction, whether it's being reduced or not in the final equation, we're going to give it as a reduction. We'll see that that's our half cell equation, and we can do the same for zinc and give them as a reduction. So each half cell represents a half equation. Notice that we've written the half equations with reversible arrows because at the moment we don't know which way around this reaction will go. We don't know whether copper 2 plus is going to get reduced or copper is going to be oxidised in our reaction. So these are half cells. I could then have a look at what would happen if I connected these two together via a wire. Remember that the metal could conduct electrons out through the metal and into a wire because the electrons will flow through the metal and into a wire. So what I've done here is I've connected those two half cells via a wire through a voltmeter. And what you can see is that nothing is happening. There is no voltage being read on that voltmeter. So we need to consider why that is. So in order to harness the electron transfer in our redox reaction between copper and zinc, we need to connect it with wires so that they can travel through the wires. Why is this not working? Let's just put down what we've done so far. So in order to make use of that energy, we're going to connect them via an external circuit. That circuit is usually a conducting wire, and electrons flow through the electrodes, which were the bits of metal, and into the wire. The wire's made of metal as well. Right? We can go back and look. We can see that it wasn't reading anything because it wasn't connected here. There's not a complete circuit. So we need to connect these two beakers to one another, but we can't connect them with a wire because we're trying to connect the solutions. Remember that our half cells were made of the metal in the solution, and the two halves have got, the two halves have got the ions and the metal at either side. So we need to be able to connect now. We've connected the metals with the wire. We need to be able to collect the ions somehow. So we're going to connect our two solutions, and we're going to connect them so that the solutions can allow current to flow. And if you remember back to high school, ionic solutions conduct because ions can move. So what we're going to do is we're going to connect them with what's called a salt bridge. And a salt bridge is very simply a piece of filter paper soaked in ionic salt solution, and so that ions can move by like a capillary action across the salt bridge. And now we can see our voltmeter is reading. Current is flowing. We have flow of electrons. We're measuring actually a voltage here, so we're measuring a push against the voltmeter from one side and a pull on the voltmeter from the other side of electrons trying to get round that circuit. Now, there is some physics involved here that is not essential for A-level chemistry, but we're using a high resistance voltmeter, so technically at the moment no electrons are making it all the way around the circuit. We've got electrons pushing against the voltmeter from one side and pulling from the other side, and we're measuring the difference between the push and the pull, measuring a potential difference. Let's have a look. We've got this salt bridge, and our salt bridge is connected to filter paper, and it's saturated potassium nitrate. That's the one I'd like you to use when you're answering. You can use potassium chloride, but there are a couple of exceptions, times when potassium chloride is no good to you because it could react with things in your beaker, but potassium nitrate is always going to work, so I'd like you to stick to learning that one. And when we have that connected, it's going to be ions that flow through the salt bridge because it's ionic, not metallic, and therefore ions is what make ionic things conduct, electrons are what make metallic things conduct. Okay, so they're connected it all together to a high resistance voltmeter which measures the potential difference, the force, and that is called the cell potential. We set it up under standard conditions, and the standard conditions are 100 kilopascals of pressure, 298 Kelvin temperature, and concentration of 1 mole per decimeter cubed for our solutions. Okay, the ions need to be at that. So we will pay attention to that later because, for example, if I want 1 mole per decimetre cubed of copper 2 plus ions, I need to make sure that the formula of the ionic substance will give me that. So if I have 1 copper sulfate, I get 1 copper 2 plus. But if I, say, took something where we had, say, copper phosphate, so copper phosphate would be Cu3PO4 twice, you wouldn't actually need 1 mole to get 1 mole per decimetre cubed of copper 2 plus, because there's 3 copper ions in that. So you would need to be careful. It would be 1/3 of a mole per decimetre cubed to get 1. We'll talk about that later. So we've ended up setting up this circuit, which we've just seen in our picture here, down at the bottom. That was our circuit we set up. And it looks like this in a diagram that we would draw for the exam. We had a strip of copper in some copper 2 plus solution, and that was 1 mole per decimetre cubed. We had a piece of zinc metal as an electrode in some zinc 2 plus solution, again 1 mole per decimetre cubed. We had a salt bridge, which was potassium nitrate, filter paper soaked in potassium nitrate, and we have a voltmeter, a high resistance voltmeter, connecting them together. So what is happening where? Well, remember that the electrons are going to flow out of the solution through the electrodes. So these electrodes, these bits of metal, the zinc and the copper, are going to allow electrons out of the reaction and up into the wire. And then the solutions, the salt bridge is going to allow ions to flow back and balance the charge, maintain the complete circuit. So when this cell is connected, what we find is if we look back here, here's my picture. My copper is connected to the red terminal, that is the positive terminal, and my zinc is negative. Now, if I connected this the other way around, the voltmeter would have a negative reading. So how do I know who's on the positive terminal and who's on the negative terminal? I connect it until I get a positive reading, and then I look who's on the red wire. The red wire is the positive wire, and the copper is at the positive terminal. So when this is connected, the copper is at the positive terminal, and so is the positive electrode. So whoever's on the positive terminal is the positive electrode. The voltmeter reads 1.1. Now those of you who've got keen eyes might have noticed that that voltmeter on that picture read 1.04. That's because the lab was not at all these standard conditions when I set that cell up. Okay, so the value varies slightly. So we've got a couple of other things to watch out for in this section. Well, what's happening? Oxidation is occurring at the negative electrode. So in our example, the negative electrode was the zinc electrode. Oxidation is going to occur there, and reduction always occurs at the positive electrode. And the standard convention, if you saw that box at the bottom of the last page, is to put reduction on the right. So the reduction's on the right, and reduction is the positive electrode. And electrons are going to flow from the negative to where they're needed. They're needed for reduction. Reduction is gain. They're going to flow to the positive electrode. So what's happening at the negative electrode? We need to write an equation for the reaction happening at the negative electrode in our copper zinc cell. Now, we've already worked out that the copper was the positive electrode, so the zinc is the negative, and oxidation occurs. So zinc is being oxidized to zinc 2 plus at the negative electrode. And then at the positive electrode, reduction occurs, so copper 2 plus ions are picking up the electrons that come through the wire towards it to form copper metal. And when you connect all of that, you get a value of 1.1 volts. Now, your typical AA battery is 1.5 volts, so we're looking a little bit short of that typical battery. What we need to understand to be able to find the best battery is how much of that force was caused by zinc's ability to lose electrons and push them away from itself, and how much was caused by copper's ability to pull electrons towards itself. It's a difference between their two abilities, it's a potential difference. So what we need to do is sort of be able to know how much of that was due to copper and how much was due to zinc, and and then pull that together in order to find different combinations that give us the voltage we want. And this idea is something called the standard electrode potential, which we're going to address in the next video.